Okay, so now we are going to cover estimation, which is quite an important function. Sorry, quite an important topic for stats too. Um, in fact, I believe most of the topic are related somehow with this idea of estimation. Okay, first of all, why do we estimate, right? Um, well, um, typically I think it's important to know the distinction between the two branches of statistics that I will outline. First is descriptive, right? First is descriptive. And second is inferential. And for descriptive statistics, basically what you do is um you deduce properties from a population. So if you're given like maybe um let's say human heights, right? Human heights and sorry, of 1,000. So boleh from here you can calculate mean, median, standard standard deviation, etc. Right? So that is mostly about descriptive statistics. Inferential, on the other hand, is you deduce you deduce properties from a sample. mm, from a sample where, for example, um, about the height kan, contoh lah, you know the mean height, uh, uh, you know the mean height, and you're interested to answer questions about uh, the population. For example, you can say that, oh, if I know if the height of, let's say, 1,000 people is like such and such centimeters can. So what is like the distribution of the height? What is the variance? What is the even other properties? How are these heights distributed, such and such? And estimation deals with this second topic here, which is why um much of the topic that we will study is also called statistical inference, which is to put it roughly lah. Basically, you're studying about the parameters of the studying in depth the parameters lah of a given statistical model. Okay, okay. So one of the most popular ways to estimate parameters are also known as the maximum likelihood estimation, right? And so maximum likelihood estimation ni, um, okay, I'll discuss what each of these terms means, right? So first, right, suppose that we have a constant theta, and this constant theta belongs to the set omega. where omega is all possible uh, values lah for theta. In other words, if given a statistical model that has a parameter theta, let omega be the parameter space, right? Okay. All right. So suppose lah, if we are interested in estimating uh, theta, let's say from a random sample, from a random sample, from a random sample, um, let us take um, observations. Take observations x1, x2, xn, which represents the random variables representing x1, x2, xn. So each of the observations are the realizations of. For example, this small x1 is the realization of this random variable capital X1. Same goes with x2 and so on. Okay. For example, okay, and then let's call our estimate u x1, x2, xn. So this is an estimate of theta, right? So if this is the estimate of theta, if we're estimating theta from a sample that is from the observations x1, x2 until xn here, then we can say that the estimate of theta is a function of the observations. Betul tak? Right. Okay. And of course, we would want the estimate to be as close to theta. Uh, Since, of course, we are estimating, let's say, one parameter theta, not uh, two parameters, not two parameters, for example, right? Theta 1, theta 2, but just one parameter. We say that this estimator here, x1, x2, xn, is also called a point estimator because it estimates this constant data here, which can be interpreted as a point, right? Okay, all right. Now for the definition of the to be used in estimation, okay, let x1, xn be a random sample, right? From a distribution that depends on one or more unknown parameters. Unknown parameters, theta 1, theta 2, theta n, right? Where each of the x1, x2, and the xn has a EDF, which is the probability density function. That's denoted by f x I theta 1, theta 2, then. So how the way we read this is that the function fxi, this is the function of xi given theta 1, theta 2, and theta m, which we want to denote that maybe the each random sample x1 until xn depends on one or more of the unknown parameters, lah, right? Theta 1 to theta m. Then the likelihood function is simply the likelihood function is um, just the joint. mm, yeah, the joint PDF, let's say, of x1, xn. Okay, L. Let's say we denote this as L, lah, the likelihood function as L. Okay, this is just x1 multiplied by fx2 until fxn. Okay. Um. Okay, I think I forgot to um share some details. Wait, some some more details into the definition. Here we suppose that let's say we construct a vector of parameters, right? Is restricted to a given parameter space, omega, right? So this is the definition of the likelihood function, lah. So, okay, so then mm, recall that recall this vector of parameters, right? If let's say uh if a vector okay, so if this vector maximizes the likelihood then then okay, then the theta 1 hat, this is the hat symbol, right? Theta 2 hat, and theta 1 hat, theta 2 hat, until theta m hat are the maximum likelihood estimate, maximum likelihood estimators of max likelihood estimators, or in short, we could say MLEs of theta 1 to theta n respectively. And the values are um, that corresponds to these estimators are called maximum likelihood estimates, right? Okay, I think this here might needs to be changed a bit. We express them in terms of functions of random variables, not the observation, hence the capital T, right? Okay. Now for some examples, okay? Let x1 equal x1 follow exponential lah, exponential distribution with PDF fx equals 1 over theta e x over theta, or x over theta, right? And x is greater than 0, and theta is a member of the parameter space, which equals to um, all positive values. Okay, how to find the MLE? Okay, so if you have this sample, right? So the way you find the MLE is first you construct the likelihood function. Since this likelihood function, you want to estimate theta, so we write it as like this, right? So we say that okay, we write like this lah. L of theta given x1, x2, the xn, right? So given n observations, x1, x2 until xn, we construct the likelihood of theta, which equals to e x1 theta, e x2 over theta e to the power of xn over theta, right? So basically, you just bar up all the PBS from the sample, right? And what you get is 1 over theta to the power of n, and then the exponent, and then 1 over theta multiplied by the sum of xi, right? Since all this x1, x2, and xn adds up, so we write it as sum over here. Okay, so to make this likelihood simpler, what we usually do is that we take the natural logarithm of this function lah, right? So if we take the natural log of the likelihood, we will have yeah, negative n log theta minus 1 over theta, and then multiplied by the sum of all the observations earlier. Okay, right? And we can be confident that taking the ln here doesn't affect our estimates in a way, because you know that the logarithm is a monotonic function, and it is also differentiable. So it, like, in a way, preserves most of the quality of the likelihood function, right? Now, differentiate this with respect to theta, and we will have n over theta n over theta plus 1 over theta squared multiplied by the sum of the observations. This sum of observation here is treated like a constant, right? So now what we need to do is to find the point uh, that the value of theta that maximizes this function here. So, sorry, this function here. Okay, so this function here. So that is easy. We can just equate this derivative to 0, because at its maximum, the derivative equals 0, right? So what that means is n over theta plus 1 over squared theta, 1 over theta squared, and the sum here will be equal to 0. And if you arrange everything up, you will have n over theta, 1 over theta squared, sum, divided by this sum, and then multiply everything by theta squared and divide it over n. You will have theta 1 over n x r, which is the same as the sample mean. Just stay remember, because sample mean is uh, just the sum of all observations divided by the number of observations lah, right? So we say that um, the MLE, the maximum likelihood estimator for theta, is theta hat equals the sample mean. And that is how you find the maximum likelihood estimator for theta. I hope that helps. Thank you.